Hi, everyone. This is Aditya, and I'm very pleased to welcome Alex Gray from IBM Research AI today as the start of our Spring 2021 section of our Ideas AI seminar series. He'll be talking about logical neural networks towards unifying statistical and symbolic AI. So Alex serves as the VP of Foundations of AI at IBM and leads currently a global research program in Neuro-symbolic AI at IBM. He received his bachelor's degrees from Berkeley and a PhD in CS from CMU. And he's an old-timer for Georgia Tech because he was faculty here before he moved on to start a company and then join IBM. He also worked at NASA. His work on ML statistics and algorithms for massive data sets has been honored with a number of research honors, including the NSF Career Award and a selection as a National Academy of Sciences Kavli Scholar, and including being a member of the 2010 NAS Committee on Analysis of Massive Data. So again, let's welcome Alex back to Georgia Tech, and really excited to hear what he's been up to, Alex. And just a reminder to everyone that if you have any questions in the middle of the talk or even at the end, please feel free to post them and type it out on BlueJeans, and I'll read it out to Alex because he can't hear you. Anyway, over to you, Alex. Thanks.
All right. Well, thanks, Aditya, and then thanks, Hasan, for the kind invitation. It's a great honor to be back, at least virtually. Maybe another time I'd love to come in person and see all the faces that I missed from the back in the day. And I'll answer all questions at the end. Hopefully I'll leave enough time. This is actually one of the first presentations of this work, so I am definitely looking forward to your feedback. So this general area, neuro-symbolic. So it was a recent talk that mentioned it at AAAI. Henry Kotz gave a nice, his own little sort of informal categorization, which I thought was nice, of the different approaches. And I've listed them here, 6 or so approaches. I have another survey talk where I go into them in a little more detail, you can see here. But more or less, these are all different ways of trying to bridge neural networks, roughly acting as the main representative of statistical AI today, and logic, roughly first-order logic, representing kind of the different kinds of capabilities in symbolic AI. So most of them, however, are just bridging techniques. I'll say what that means in a second. But they almost always have these kinds of goals. So one is understandability. You could say this is one of the main things holding back current AI, default AI, which more or less end-to-end deep learning, from many more, let's say, critical tasks. The ability, but understandability is closely related to controllability. And then the second thing is just generalization, but sort of generalization plus, not just sort of small deviations from a data set, but larger deviations, you could say, to different tasks and large changes in the situation. And why is because the hope is that by injecting knowledge, which is generally cast in terms of logic, at least in the symbolic AI days, then you can have a more general picture of how the world works that you can reuse in different ways. Okay, and finally, reasoning. Once knowledge and reasoning sort of go together, or roughly speaking, how you might define symbolic AI, and more complex problems would seem to require a kind of reasoning. So now, however, the current batch of things, I'll argue, sort of are missing some properties. One is the understandability is not arguably not a true understandability just by having logic side by side, more or less, with black box models. Because you still have the black box, and almost all of these things really have maintained two representations at the same time. And many of them, most of them, are not compositional. And arguably, then they're not modular, and you can't reuse knowledge very easily. And thirdly, the reasoning that you get with many of these approaches, typical approaches, is actually not true reasoning, not rigorous reasoning, but sort of reasoning-like. Okay, or to work on simpler logics, not for first-order logic. Okay, so you could say what we're doing here, introducing a seventh type of neurosymbolic combination pattern, which is perhaps a surprising one, is to show that there is actually an equivalence. There's a very big overlap between neural nets and logic, which may be surprising, where they are the same. And by doing this, we'll actually have one representation, not two, and which will have the capabilities of both. Hopefully, we'll preserve the key capabilities. It will be compositional or modular or reusable, because logic is that. And it's true reasoning, as you can do with true logic. Okay, so that's what we're going to try to do. All right, and here's some more information. Bottom left here. So let me tell you a little story. This will take about half the talk, and then the rest of the talk I will talk about extensions. Okay, I'm going to lead up to the punchline of how exactly it is that we can see that neural nets and logic are actually not, two things that are wildly opposed. There's a sense in which they are the same. Okay, so I'm going to take you through 8 easy mental steps to build up to that punchline. So first, we go back all the way to the original neural net paper, the very first one, 1943, McCulloch and Pitts. What they pointed out was that a sort of threshold type unit can do all of the logic gates and represent all of the kind of 3-ish sort of ones that you need for convenient representation of knowledge, arguably, or and, or, and implies. And then you have to have a not somehow. So this is how you do it with this kind of a gate. Now, it can take any more than 2 inputs. Notice that it doesn't have weights exactly like a modern neuron, and the activation function was a step function at this time. Okay, but it shows something neural-like can implement logic. Okay, that was the basic idea, which more or less hasn't been directly built on since then. I always thought was odd. So, next in the historical evolution, you could say you add weights. You still have a step function, the perceptron. To interpret this as logic, there is still an interpretation. There's a region of the weight space in which, say, it acts like an and. There's another region of the weight space in which it acts like an or, so on. Okay. An and is where, all of the, you need everything to be true, for the output to be true, and if even one is not true, you don't get a 1 at the output. Okay, so you can set that up with some inequalities. All right, so far we still have a connection between neurons and logic. Then, of course, the celebrated leap is go to multiple layers. You need back prop, and you need to be able to have differentiable neurons. And so now the step function is replaced by something softer version, you could say, the sigmoid, for example, or more recently, the ReLU or rectified linear unit. So you can have derivatives. Now, however, from a logic standpoint, you now have lost something, which is that now the output values are somewhere between 0 and 1, but not strictly 0 or strictly 1. So you have to do a little thinking now about how if you want to maintain the logic connection. Okay, so, so it's sort of gone at this point. Now, what we can do, though, is we can say, well, at least near the end, let's look at the sigmoid, at least near 0 and near 1, we can sort of say, if we want to enforce that the thing acts like a logic gate in those regions, near we define by some distance alpha, then you can just enforce these kind of constraints and make it act like classical logic. Okay, so the new addition here is now you have some constraints on the weights. Okay, but that's not quite enough. We still also want to, we still have to think about what happens in between, in this region in between. Okay, well, before we do that, as long as we're going to add constraints, let's add some slack. This is typically what you do when you set up some kind of machine learning thing with constraints. So here's a version of the optimization problem with slack variables, and these govern a degree of adherence to logical behavior. So if you set the slack parameter high, then you don't have to obey logical constraints. Okay. Also, they can sort of act as pruning of weights, that function. All right, so that's sort of just part 2 of setting up a constrained version of a neural net. Now, but for this region in between, so you may be thinking, some of you who've heard of real valued logics, hey, there are real valued logics. So now, in fact, by real valued, I mean their output or truth values are not just 0 or 1, it can be between 0 and 1. So, of course, many have heard of Zade's logic under the name fuzzy logic, but this is all actually earlier than Zade, which was 1965 or so. So, in fact, it goes all the way back almost to the beginning of mathematical logic. So, in fact, Boole has had some version of a probabilistic logic himself. So, but here are some common real-valued logics. These all define the equivalent, the analog, you could say, of and, or implies with, some function. Okay, now they have different behaviors in between 0 and 1, but all of these have the property that at 0 or at 1, they're the same as classical logic. Okay, so good. There's already a rigorous way to talk about logic where values can be between 0 and 1. Let's look at one of these. It's a very common one, Lukasiewicz logic. Now, here's a certain definition for and, or, and implies. You notice we write and or with these funny symbols now to show that they're not exactly and or, they're analogs or generalizations. Okay, but if you look at a plot of and here for the 2 input variables and the output, it happens to be the same as the ReLU activation function. So this is a fortuitous coincidence, you could say. We can already see some kind of correspondence, hopefully, now. Now, between logic and a neuron. However, one thing that's missing still is weights. A neuron has weights, a modern neuron. No problem. What we'll do is we'll just extend, say, the cashier's logic, but it can be done with any of these logics in a sort of natural way, that puts weights on the inputs. Weights sort of signify the importance of an input. Okay, and you can define a rigorous logical semantics this way. And fairly natural. And again, this can be done for a sigmoid. This can be done for any of those other real-valued logics. So more or less any common activation function, you can make this sort of logic version, and any common real-valued logic, also you can sort of make the equivalent activation function. We need one more thing to finish the idea of a logic. We need inference rules, not just how you represent statements, and the components of statements, but what do you do with a statement to get the truth value of another statement? So in classical logic, you may dimly remember from your AI class things like modus ponens, so which is sort of an obvious kind of inference rule. It says if you know P is true and you know P implies Q is true, then you can infer Q. Okay, so that you can apply and under those, whenever you know P is true and P implies Q is true, so on. So this is what we mean by inference rules, logical inference rules. Okay, so great. That's classical logic, but what are the inference rules for real valued logics? And when you start to think about inference, you want to know, of course, you're doing correct inference or rigorous inference. How do you characterize that? Well, the typical thing is soundness and completeness. So, and it turns out this had not been established fully for real valued logic. So that was a bummer when we realized that. Despite how old it is and mathematical. So what had been established is the soundness, if you remember, is a logical system, which is a logic and its inference rules, is sound if and only if the inference rules admit only valid formulas. So by applying in whatever the inference rules are in your set, you can never get a statement that's incorrect. Complete means any statement that's correct, you can get to it eventually with some application of inference rules. Okay? So, but it turns out strong completeness had never been established. So, but turns out Ron Fagan, oops, I have a little vestige from an older talk, but you can see in this, it's an archive preprint, Ron Fagan, logician and National Academies member, showed this recently. So this is great. This gives us a strong foundation for using real valued logic. Okay, now this is a bit of a sidetrack because we had to do something very fundamental in order to proceed along this that applies well beyond this goal, which is about neural nets. This sort of applies to any situation where you want to use real valued logic. Okay, but great. Now, if you look at this paper, it shows a decision procedure, which is how you establish whether a statement is true or not under your logical system. And that thing is, at least for two common logics, a mixed integer linear program. And that's great that you sort of know how to compute that, but it's expensive. Further, we want something that's neural net-like. That was our hypothesis, is that there's some version of logical inference that maps to a message passing type algorithm like you have in neural net infrastructure like PyTorch. Okay, and so we can imagine that, but let's look at what that would take. So here is a neuron. Let's pretend this neuron is implies instead of and for a second. Now, and let's think about the inference rule modus ponens. You remember that one. So say there are two inputs at the bottom, P and Q. Then what modus ponens says, and then the output is P implies Q. It says if we know P implies Q is true, meaning the top variable, Y, and we know one of them, let's say P, we want to say that Q is true. That's the equivalent, actually, of going backward through this neuron. You could say, because it's, the neurons normally go forward, right? So it's asking about the value of Q given P implies Q and P. So, okay, so maybe we can do that, because if your F activation function is invertible, then you can just figure out an input from Y. Now, okay, now assuming you can do that, your activation function lets you do that, then you can just define what it means to go backward, and then you can define a propagation scheme that show here. It goes up and down through neurons and does the equivalent of logical inference. Okay. Now, there's a caveat here. So depending on your activation function, you may not get a unique X given a Y. So, but you can always get bounds. And that was sort of a messiness we didn't like at first, but then we realized it's actually kind of a plus, because it introduces the idea of bounds on truth values. And that turns out to be important for real life, because you don't always have full knowledge of truth values. In fact, arguably, for most situations, you only know a few truth values, and most of the rest of the world, all the variables that represent everything else in the world, you don't know their truth values. Okay, so this is very important for sometimes talk about this in terms of the open world assumption, meaning that there are a bunch of variables in the world, and you don't have to know what they are, their values. Okay. Turns out most neuro-symbolic approaches, sort of in their formulation, have to assume the closed world assumption, which is that if you have a statement that's missing, then it's false, and that's of course unrealistic. Okay. Now, I'll just mention a side note here, which is that you may be asking about or wondering about probabilities in your mind. There is a mapping to probabilities, so I'll come back to that later. Okay, now this is just to get a better picture of what this would look like as a method. So now you have logic statements. You have a bunch of logic statements, get from somewhere, humans or elsewhere, which we can talk about, say at the top. This basically is saying that a neural network can represent the syntax tree of those statements. And the facts at the bottom, like let's say one of these logic statements, like the middle one, is saying something like, if X is born in a place A, X is a person, is born in a place A, and the place A is part of another place B, for example, a city being part of a country, then X is also born in B. So say if X is born in New York City, X is also born in the United States. So that's a logic rule. And the facts sort of that you might observe are in various instances, say in GBpedia, which is a knowledge graph of various people being born in different places. Okay, and so the input to this model is sort of relational data, like you would have natively in a relational database, or knowledge graph data. Okay, and by the way, regular supervised learning tabular data is just a special case of this. Okay, so but now, because we have this ability to do inference in any direction, so it's not necessarily like a constrained to be like a normal feed-forward neural net. Have a definite output node and some definite input nodes. Any node can be my output node, and any subset of nodes can be my outputs, and any subset of nodes can be my inputs. I call this any-task learning. And whatever current snapshot of the world and all of its variables, inputs and outputs, I can just call a world. That would be the equivalent of a row in a training set, the normal training set. Okay, so roughly speaking, you could say this is a generalization of normal supervised learning. And then unsupervised learning is where you could say you predict everything. Okay, so what does the optimization problem look like? So here we write our normal loss function, which is this leftmost term, whatever that is, hinge loss or squared error or whatever, that talks about, measures your gap between your target values and predicted values. Then we have this other term which we add, we'll call contradiction loss. And it's there to ensure that all of the variables are sort of consistent with each other, that are logic statements. Remember, logic statements can be wrong or inconsistent with each other. I could have a fact somewhere in my knowledge base that says Barack Obama is the president of the United States for whatever reason, and then I can have another one that says someone else is the president. So, so that's okay actually in this model. Unlike in classical symbolic AI, where that would grind your whole system to a halt, can't proceed the logical inference, you have a contradiction. Here, we simply sort of minimize the amount of contradiction. Another way of looking at this is sort of what glues together all of these variables or tasks. This term tries to make sure that they're all sort of working with each other. Okay. And then, but now of course you have and you have these constraints we saw from before. So this is some kind of constrained non-convex optimization problem. All right, so we have a number of different ways we've tried optimizing this. We have a very basic vanilla version in the original write-up, Frank Wolf. We have a better version called double description method. We utilize something called the double description method. And I'll say a little bit more about this third one, a much fancier one. Okay, so that's learning. And so if so you know, we've got something that, if you look at it as a neural net, can learn weights, like a neural net. But if you look at it as logic, the logic is weighted, and you're learning the weights on the logic. Okay, so it's like learnable logic. So here's the punchline. So in this box here, so these aren't some funny activation functions or anything. These are normal activation functions that are used today in modern neural nets. So a standard deep learning model, recurrent even, with the extra modification of constraints, although it's not necessary. That's actually just to make it work like classical logic. Okay, but it equals a set, is equivalent to a set of logic statements in a weighted real-valued logic. Okay, that's the equivalence punchline. And then inference, the other piece of the puzzle, standard neural net forward inference plus the addition of a ability to go backward, definition of how you go backward, is the equivalent of logical inference in a weighted real-valued logic. Okay, so this might be surprising, but it's basically saying that you can interpret a neural net, any neural net, as already doing logic. So, but then you can constrain it to act a little bit more like classical logic if you want, fully like classical logic if you want. Okay, so that's why I say classical logic is a special case, and true logical reasoning is a special case. Another thing that's a special case, of course, is a regular neural net with no constraints on anything. So, and you can vary between the two. You can have parts of the network that are full black box neural nets. For example, lower level sensory inputs with no constraints. And you can have parts of it, for example, upper parts conceptually that obey logic or concepts. Okay, so we actually haven't played much yet with that full hybrid. So far, we're actually just treating everything as logic. Okay, so that'll be an interesting area to explore. So, okay, and you can mix precise and imprecise logic statements. Now, if we go back and compare the other common neurosymbolic AI ideas, probably the two most common ones are the one with the most citations and most mature, arguably, is Markov logic network, and that was early 2000s, 2006 or so. There's been a lot built around that. That's based on, and there a few other approaches also built on the idea of Markov random fields. And there, logic statements are encoded in a Markov random field. It'll become a clique. A logic statement becomes a clique of terms in a Markov random field. Now, what happens there is you can see in this picture, all these three pictures are showing the same example and how they're encoded. You've actually lost in the actual MRF, you've lost the logical connectives. They're not in the model anymore. Okay? You maintain them, however, somewhere, so that you can understand the variables. And you can, if you look at a new data point, you can evaluate whether it's true or not for that data point. So that's what I mean by subtly, they're actually maintaining two representations. Okay, but the learnable representation does not actually have all the full information of the logic in it connected, and it's not compositional anymore, because this clique, if I have 10 different logic statements that all have the same variables in them, they all boil down to the same clique. So the other major idea, you could say, or common idea, represented in many papers, is the idea of the basic representation not being, not having a one-to-one mapping between concepts and neurons, but a distributed representation. So, or sometimes what's said is there's a disentangled. What we're talking about in LNNs is a disentangled representation versus an entangled representation. In other words, a concept like grandmother is represented somehow over maybe 10,000 neurons. There's a single neuron that represents grandmother. Okay, and that some of that intuition comes from neuroscience and so on, but the idea is that a logic statement is a point in an embedding. Now, what happens though is that, well, at least logical inference is the result of somehow end-to-end training, and it sort of becomes the equivalent of real theorem proving in the limit as the number of examples goes to infinity. So that's why I say it's not quite hardcore theorem proving. Sort of like logic-like, reasoning-like. So, and this would be borne out, say, in a study on or empirical evaluation in theorem proving problems, which we have in the paper. So an LNN, bottom one, is actually a direct translation between the logic statements and the neurons. It's disentangled and does true pure theorem proving. Okay, so that's the end of that story. That's just to tell you what an LNN is, and why it's different properties, and I hope advantageous ones. Now, the embedding, just a side note, the embedding idea I think is kind of interesting. It has some interesting properties that we do actually want also in the model. So one of the threads we're exploring is adding in embeddings as well. Embeddings acting as sort of your intuition, you could say, and filling in the in-betweens where you don't have enough knowledge or something, but you can still do your logic as well, as opposed to only relying on these sort of very rough, fuzzy concepts. And that's there's probably multiple ways to do that would be fun to explore. So let me tell you about the next kind of big thing here, big thing we're excited about anyway, and how we show the value of this, so far how we've shown the value of this. So we wanted to take a hard problem that end-to-end deep learning for today's default AI really is not very satisfactory for, to show why you need this extra power of knowledge and reasoning. So here is something that is actually very simple for humans, And it's on an NLP sequence of harder and harder problems. So question answering, this is question answering for sort of simple factoid questions. Okay, so obviously NLP can be much more difficult than that, or tackle more difficult things than that. But perhaps surprisingly, this simple kind of question, was Roger Federer born in the United States? This, or take a data set of questions like that. Today's end-to-end deep learning type approaches, do terribly on such data sets. Something like 33% F1 or so. So we like this kind of thing as a challenge. So, and even though it may seem like an easy question, this particular question requires reasoning. So, because let's say you have some knowledge, you're given the ability to look at a knowledge base in this setup, and let's say we use Wikipedia, which encodes in a knowledge graph or triples the facts in Wikipedia. Somewhere in there it says Roger Federer is born in Basel. Okay, and somewhere else it says Basel is part of Switzerland. So, but the question is, was he born in the United States? Now, so you have to put together a few facts in the right way to answer no, because you have to know that, well, the United States is also a country. If you're born in one country, you're not born in another country. And if you're born in Basel, you are born in Switzerland, and so on, and therefore the answer is no. Okay, so now look at end-to-end deep learning. What does it do for such a thing, for this kind of a problem? It basically selects from pre-canned existing sentences as candidate answers. It can't actually extrapolate to answers that don't appear in the training set at all, or very poorly anyway. And generally systems are demonstrated on one data set and kind of overfit basically for one data set. And there's generally no reasoning. And you could say there's no understanding because there's no attempt to map. I sort of define, at least intuitively, understanding as having some abstract concepts, principles. And there's no attempt at that generally. Just maps from the input to the output, the words of the question to the words of the answer. So further, it relies on a lot of labeled examples, and in these we have as little as 400 questions and answers in the training set. Okay, and then of course, if you make it even harder and ask the system to explain why it gives that answer, there's no way to do that that's effective that I know of with deep learning. Okay, and here, by the way, different kinds of reasoning you could say that appear in, or they're represented by different kinds of questions. Even simple questions require certain kinds of reasoning. So what do? We take a different approach. So instead of going directly from the form of the input to the form of the output, you could say we require an intermediate step, which is you translate the input, which is words. And by the way, you can imagine an analog of this for vision or any other modality, speech. I'm going to first map it to logic, the underlying concepts. And that is often called semantic parsing. And then once you have it in logic form, you understand the question in logic form, then you can apply reasoning using all the facts you have to answer the question. And then we take, it's actually harder than it sounds. So we use some intermediate representations, including AMR and Sparkle, to manage the graph database. Okay, and this system here is a modular system and involves or allows the use of state-of-the-art methods in all of these different parts of the problem. And we ourselves sort of have the state-of-the-art methods for some of those parts, the key ones, like AMR parsing, relation linking, and near state-of-the-art for entity linking. And you can see here we achieve the state-of-the-art. We beat the state-of-the-art for 2 of these KBQA data sets at the same time. So that in itself is unusual, that one system can actually generalize to more than one data set. Arguably, and this is a big claim, but I at least haven't seen yet a neuro-symbolic system that has a win over the state-of-the-art in anything that's like a completed benchmark. So I want to say hesitantly, this is maybe a first win for neuro-symbolic, any neuro-symbolic approach. Now, part of the hope for gains here that we achieve something that's understandable by humans, as opposed to 10,000 neurons in the neural net. So here, this is just flashing some steps that you would go through, more comfortably as a human. But this is a way of showing the steps of reasoning and which knowledge is incorporated, or is being relied upon, and which reasoning steps to answer this question. And this is why the system is saying no. Okay. Now we have a lot more that we're planning to do here. This is just a first cut at how you would explain the model and its reasoning process to a regular human. Okay, which is sort of inconceivable, I think, for today's machine learning methods. Now, three more things here. So a key aspect of this is the inference process, which, of course, as you know, is for logic, is expensive. It's combinatorial in the worst case. Now, however, we are showing here that we can tame that, perhaps surprisingly, with learning. In this case, it's reinforcement learning. And we show on benchmarks of theorem proving, which basically are all about speed. We show that we beat even mature, handcrafted theorem provers like E. You've heard of that. Okay, so so this is a way we'll be approaching the inference problem. And what you're learning here is the search procedure, basically, that you have to use. You have to use some kind of search procedure in inference. And this, just as humans sort of learn patterns of how to reason more efficiently than just doing a big combinatorial search. That's what this is doing. Okay, now another aspect of this is, so far all I've shown you is that you come with a knowledge graph and that becomes the neural net. So whatever knowledge you put in becomes a neural net. But of course, you next want to figure out a way to obtain knowledge, obtain new nodes automatically in your network. And that becomes the equivalent of logical rule induction. So another name for that is inductive logic programming. And so we have a way to do that, compare that to traditional methods of ILP, but also more modern methods, most of them based on embeddings. And we show that you sort of get some very difficult to interpret rules. Here's an example here of what the ground truth rule is in a certain problem. And you get a sort of big pile of other rules, often with these methods. And we show here that the rule that we learn, this approach is actually pretty crisp, very close to we give some small weight to some irrelevant terms, but it's quite small. Okay, so you actually can learn high quality rules, and sort of is the state of the art in versus neurosymbolic methods. Now, just a little bit about the optimization problem. It's actually it's a little bit harder than some other learning problems. The objective is non-convex, so that's common these days. But L and U, these bounds are non-smooth, and the constraints actually contain nonlinear coupling. So, but here's a sort of fancy approach to that, using a variation of ADMM, which, by the way, has a side effect of making it not so hard to be distributed. What we show here, state-of-the-art in convergence rate, is scalable with the number of constraints, and compared to other optimization approaches for this kind of a setup, it appears to be state-of-the-art. Okay, one more thing I want to show you. Well, I'll just go real quick, but we've just started on the idea of, if you think of this as a beefing up of deep learning by adding knowledge and reasoning, what would be the deep RL version of this? And we call it logical optimal action. We're testing it out on hard problems like text world, where you have an infinite number of actions. We want to see, our hypothesis is, can we use knowledge to dramatically reduce the very high cost of reinforcement learning? And here's some initial workshop results for a simple problem like blocks world to show an advantage. Here we're representing the policy as rules, and we use this rule induction I just showed you. Now, let me tantalize you a little bit with this. You may or may not have seen a Twitter war between Yashua Bengio and Jerry Marcus not long ago. I think it was last year. And basically, I went back and forth about what the properties of an AI system should be. And I put together a sort of distillation of the different things that they each said. And, it's not rigorous, it's all qualitative, it's subjective. But they sort of represent, roughly speaking, the hardcore neural net view and the hardcore logic view, or some classical AI view. If you put together this list, it's sort of both. And so this is showing again, qualitative, arguable, debatable assessment of symbolic AI alone, statistical AI alone, and these two major kinds of approaches to neurosymbolic. And then L and N. Of course, I'm biased, but one reason I'm excited about L and N is that it offers a path for almost all of these things. So we're either very close on some of them that I've marked here. We sort of have a way for all of them, except for the very last one. That I would say we're still, but that's arguably the holy grail of that no one's achieved, which is true, one shot or few shot learning in very disparate from the situation, generalizing to a situation that's very disparate from what you've seen. Okay, and here's some ongoing directions. I'll come back to this for anyone interested, but we're seeking collaborators. It's a pretty large effort, so we have people working on all of these things. We're looking for help on all of them. HPC optimization, a huge amount of things we want to do on the natural language side. We think there's a way to generalize Bayes nets and graphical models. This approach, I mentioned incorporating embeddings in various ways. Many extensions to higher order logic, including all of the different logics that people have, major logics that people have proposed to handle major things like time, space, and so on. Want to acquire knowledge automatically. The best way is by reading documents, arguably, by doing semantic parsing. And this sort of key maybe, we think, for the last that I mentioned, learning with much less data, compositional multitask learning. Okay, so philosophical shift here. The human in the sort of standard black box approach really puts his or her effort into labeling data, which is relatively simple and thought-free. Now the model, I draw it as, having a lot of sort of identified concepts in it, maybe some pieces of it that are little black boxes for certain mappings between variables. But that structure comes from knowledge, and the human in this model goes back and forth, looks at the model, its performance, maybe adjusts the knowledge, sees where more knowledge is needed, and so on. The human plays a bigger role here that's generally thought of as bad in the current paradigm. I think of it as good because we're not achieving everything we want to achieve with AI. And adding humans, maybe not such a bad idea. So this changes the whole relationship. It relates to all the fears around replacing humans and so on as well. Okay, so that's it. I failed to leave as much time as I wanted to for questions, but hopefully people can stay a few more minutes. There's a summary of the basic ideas and where to find out more. And with that, I'll stop here. And I'm looking at the chat. Questions.
Oh, we just had one question posted.
Okay. Hey, David. Yes, good question. The question is, how well will all the existing architectures and ideas from deep learning transfer? We haven't explored that much yet, and it will be very interesting to see. But I anticipate two kinds of things. One is you just wholesale take, any existing thing like a transformer architecture or something and use it as a subnetwork. What you need is a training scheme that allows you to train the whole thing, including the parts that need to meet constraints and the parts that don't. And you have one optimization scheme. So that we show soon, possibly with help or participation for anyone interested in that here. But the other way is to make a true LNN sort of version of that. For example, LSTM. It uses an idea of gating to make the whole. That's what made the whole thing work. That made recurrent neural networks work, you could say. So now, just an idea, but that maybe can be translated directly to logic gates. So and give an actual interpretation to that gating mechanism. So there might be sort of logical versions of the same architectures that are successful today in deep learning, or you can simply plug them in as sub networks. It still needs to be seen empirically that works well, but that's something we would be exploring. I thank everyone for your time and attention. Looking forward to anyone who finds any of this interesting and would like to chat. Well, with that, take care, everyone, and thanks.
Thank you, Alex. And everyone stay tuned for more updates on future seminar series this semester. Thanks, everyone.